Welcome back. We're continuing in Chapter 10, Unit 6. We're going to do the 10-4 extension today. This is one after we did Section 10-4. This is intersection and union of sets. Targets today. We're going to find the intersection union of two or more sets, and we're going to be able to prove that two sets are or are not subsets of each other. So we're talking about intersection, union, and subsets today. Have these goals, targets in your notes for tomorrow. Okay, so here's some vocab and some key concepts that you should have. This comes straight from your textbook, so you can copy those down as well from the 10-4 extension. So right after 10-4. If you want to know, we're going to look at set first. A set is a collection of disjoint objects. Each object in a set is called an element or a member of the set. A set is denoted by enclosing its elements in braces. For example, if A is a set of positive integers less than 5, then A is 1, 2, 3, and 4. And those they have little brackets, not parentheses, they're the little brackets. We'll draw those as well. We'll practice in here in a minute. There are two very special sets that are often used. The sets with no elements is called the empty set. I've also heard it called the null set, and it's denoted by a 0 with that diagonal line through it. The set of all elements under consideration is called a universal set. So the universal set is U. And that means everything in that whole realm of possibilities. Now here's some drawings that may help union, intersection, and complement and other things of that nature make a little more sense. You might want to have this in your note just as a reference. So if U is a universal set, and that's the whole rectangular box, and A and B are just subsets of U, then the union of the two sets, A and B, is written A, looks like a U, right? B, and is the set of all elements that are either in A or B. So notice everything that's either in A or B is shaded. The overlap, things just in B, things just in A are shaded. Notice that it's all white outside of the two egg-shaped or elliptical shaped objects, ellipses or whole circles here, egg-shaped, let's call them. Everything else is blank. Anything not in A or B is not included. Anything in A or B is fair game. Intersection. I think intersections are where things cross, right? If you think of an intersection of two streets, it's where they cross. Okay, and that's the same when we look at intersection. Intersection, you take that U, flip it upside down. A intersect B, it looks more like an N to me, or an upside down U. And it's a set of all elements in both A and B. So it's a much smaller set because it's whatever's shared between A and B. That's the intersection. Okay, nothing else is shaded. The complement of a set is written A with a bar over it. And it's everything that's in the universal set, but not in that original set, in this case A. So notice the complement of A is everything not in A. So A is white, the oval for 8 is white, and everything else is shaded in. Okay, so that is some terminology. If you miss any of that, pause it, go back, write it down. But you're going to want that for your notes. So we're going to do some operations here. Some of these problems, let's set U is the set of all integers from 1 to 10. So our universal set is going to be just the numbers from 1 to 10, the integers from 1 to 10. So let's write that out. Sometimes it helps again. Sometimes, like if it says all real numbers, obviously I'm not going to write out the list of all real numbers. But something find out like this, we're just practicing right now. That's our universal set. No other numbers exist except 1 through 10 integers. Okay? So we got set A is 1, 2, 4, and 8. B is 2, 4, 6, 8, and 10. Find the indicated set. So for A union B. Well, that's what's in A or B. So we're going to pick out our A. So A is 1, 2, 4, and 8. 1, 2, 4. And 8 is in both, is B as well. What's the only one in B that is not in A? Well, that's 6. We've said 8 already, and 10. So the union is everything that's in A or B. And these are the braces the way I draw them, but the brackets are not parentheses. Okay, so A union B. If it's in A or if it's in B, then it's fair game and it goes into the set. And so you see how that differs with A intersecting B. A intersecting B, that's the only ones that are shared that are in common. So we can see that 2 is in both. We can see that 4 is in both sets. And we can see that 8 is in both sets. We do not include 1. We do not include 6 or 10 because those are only in either just A or just B. For problem C, it's going to ask us to get out of the way. For C, it's going to ask us to do the complement of A. So anything that's not in A but in the universal set. So the complement of A, for this case, well, 1 is in A, 2 is in A, but 3 is not in A, and it's in the universal set. 4 is in A, 5 is not, 6 is not, 7 is not, 8 is in A, 9 is not, and 10 is not. So this is the complement. This is the complement of A. And D, here's a tricky one. Complement of the union of A and B. We already found the union of A and B, so the complement would be everything from part A that is in the universal set, but not in A union B. So 1, 2 is in there, but 3 is not. 3 is not. 5 is not. 7 is not. And 9 is not in the union of A or B. So 3, 5, 7, and 9 are neither in A or in B. So that is union, intersection, and complement. The last concept from this lesson is subset. Things are subsets of each other if one thing completely fits in another set, then they are subsets. So if one set of objects completely fits inside of another set of objects, they are subsets. In math, complex numbers are the universal set, if you will. Okay, imaginary numbers are a subset. Real numbers are a subset, but all real numbers are subsets of complex numbers because every real number is also a complex number. Imaginary numbers are subsets of real numbers because every imaginary number is also a complex number. Integers are subsets of real numbers. Every integer is also a real number. Every rational number is a subset of an integer. Every integer is a subset of rational numbers, other way around. Because every integer is also a rational number. Rational numbers are a subset of integers. So that's when we're looking at subsets. In the real world, you can think of everybody in my 4th hour is a subset of students at John Glenn High School. Everybody in my class is also a student at John Glenn. Okay, so everybody belongs to that. My Algebra 2 students, I'm the subset of all Algebra 2 students at John Glenn. Okay, so it's any one group that can fit completely in a larger group, basically, as a subset. Let's do it with some number examples down here. Let A equal -2, 1 square root of 3 pi, B 1 pi 5, C -2, 1 3 pi 5. Is B a subset of A? So in order for B to be a subset of A, everything in B has to also be in A. So let's look at this. B has 1. Does A have 1 in it? Check. B has pi. Does A have pi in it? A does not. So our answer, we can stop right there. The answer is no. Pi is not in A. Okay? You can also say 5 is not in A either. So that phi is not in A or phi. Okay, we just need one number or one value to not work, and it's not a subset at all. Is B a subset of C? Well, let's look. B. 1 is in C, pi is in C, and 5 is in C. So yes, all numbers of B are in C. Is C a subset, here's a tricky one, of A union B? So we have to do a little side work. First of all, we have to do A union B. A union B is going to be everything in A and everything in B put together. So that's -2, 1, square root of 3, pi, and 5. So is C a subset of that? Well, here's C. -2 checks for both. 1 checks for both. 3 does not. 3 is in C, but it's not in A and B. The other ones, they all work. So all it takes is one value to be off, and it won't work. So the answer to this one is no. 3 is not in A and B. Okay? So that's subsets. Every value of one set has to also be a member of the bigger set. So did we hit our targets today? I believe we did. We can find the intersection and union of 2 or more sets, and we can prove that 2 sets are or are not subsets of orphans. As the notes for tomorrow, see you in class.